If you just for a second think about what's happening inside your head right now.
Uh-huh.
You have billions of neurons all firing these tiny electrical spikes.
Right.
And that's creating your thoughts, your consciousness, everything. It is by far the most powerful computer we know.
And it runs on, I mean, an absurdly small amount of power. We're talking less than a nightlight.
How much exactly?
About 20 watts.
20 watts. That right there, that's the biological benchmark. And that incredible efficiency is why we are doing this deep dive today.
Exactly.
Our mission is to explore what's called neuromorphic computing, or NC. It's a computer architecture designed to, well, basically throw out the old rule book.
The power-hungry one.
And instead mimic the human brain.
And this deep dive is really about getting you up to speed on this, well, this revolutionary path forward. We're going to break down the why our current computers are hitting a physical wall.
Then the how.
Then the mechanics of these things, called spiking neural networks, and then the actual hardware, the components like memristors, that are making this synthetic gray matter a reality.
So this isn't just about different software.
No, not at all. This is about rebuilding the machine from the ground up.
Okay, let's start there with the immediate problem. Why can't we just, keep making our traditional computers faster? What is this fundamental wall we keep hitting?
Well, we're hitting a wall of physics and architecture, really, at the same time. Today's computers, the one in your desk, the servers in the cloud, they all suffer from these massive inefficiencies compared to the brain.
Like what?
Huge power consumption, for one. They're slow, complex, sort of brain-like tasks. And most importantly, there's this data traffic jam.
The famous von Neumann bottleneck.
The von Neumann bottleneck, exactly. You have the processor, the CPU, which is super fast, but its memory, the RAM, is physically separate.
It's like it's in another room.
It basically is. So the CPU is constantly having to shuttle data back and forth across this bus. And every single trip wastes time and, crucially, burns energy.
And for something like training a huge AI model, that back and forth must be enormous.
It becomes the single biggest power drain in the whole system.
Yeah.
It's just wildly inefficient.
Which is so striking when you put it next to the brain. You said 86 billion neurons.
86 billion neurons, all processing in parallel, all learning from these tiny, tiny signals.
And the key is that the brain doesn't have that separation.
Right, that's the whole point. In the brain, memory and computation are integrated. They happen in the same place.
At the synapse.
At the synapse.
The
synapse is the connection and it's the memory. So neuromorphic computing tries to copy that exact structure.
Okay, so if that data traffic jam is the real energy killer, we need a new roadmap.
We do?
And that roadmap, the how of all this, starts with spiking neural networks, SNNs.
Absolutely. And you have to understand, SNNs are a totally different way of thinking from the neural networks everyone uses in AI today.
How so?
Well, conventional networks use continuous values. Think of it like a constant river of information, always flowing.
But SNNs are different. They're event-driven. They only care about the spike.
Exactly. A binary event. It's either on or off. A neuron fires or it doesn't.
And this is where the timing comes in.
This is where timing becomes everything. It's a concept called temporal encoding. The information isn't just in the strength of the signal. It's in when the spike arrives. The rhythm, the frequency. That's the code.
That's the brilliant part, because it means most of the time the system is just silent. It's quiet.
It's quiet. It only uses energy when there's something new to say when a spike arrives.
Which is where the huge energy savings come from.
Precisely. A normal computer is running on a clock. It's constantly checking anything new, even if nothing has changed.
Wasting energy with every check.
Right. But an SNN only burns power to communicate a change. It operates on demand.
So you've just structurally eliminated that von Neumann bottleneck. There's no need to go back and forth to some central memory bank.
You've got it. Each artificial neuron has its own little bit of local memory. The computation happens right there. And the synapses themselves, they store the connection weights, just like in the brain.
And they can change over time.
They strengthen or weaken depending on how they're used. It's learning, built right into the hardware.
So we're really moving from like a factory assembly line to a decentralized nervous system.
And to make it even more brain-like, a lot of these chips use analog or mixed signal computing. They aren't purely digital ones and zeros. They mimic the actual kind of messy flow of electricity in biology.
Which gives you even more power efficiency.
And incredible density.
Okay, so this idea of memory and processing being in the same place it's fascinating. But what's the actual physical component? I was reading about something called a memristor.
Ah, the memristor.
It sounds like something out of science fiction. Can you explain why that little piece of hardware is such a game changer?
The memristor is the key. It's what makes the whole architecture work at a physical level.
Because it's not just a simple on-off switch, like a transistor.
No, it's much smarter. A memristor is basically a resistor that remembers how much electricity has passed through it before.
So its past determines its present.
Exactly. And that history dictates its current resistance.
Right.
That remembered state is what allows it to act as a true artificial synapse. It stores the connection weight right there.
But, flash memory also stores things. What makes this so different?
Two really important things, non-volatility and analog storage.
Okay, what does that mean?
Non-volatile means it holds its memory even when the power is off, unlike RAM. So you could have an AI that just wakes up instantly, fully trained, no boot-up sequence.
An analog?
It stores that memory as a spectrum of resistance, not just a 0 or a 1. That's incredibly dense and power efficient compared to digital storage.
That just simplifies the whole system.
Massively. And then you arrange thousands or millions of these memristors into these huge grids.
They're called crossbar arrays, right?
Crossbar arrays. And that's how you get the massive parallel processing. Signals can travel and interact across thousands of points all at once. It's like replacing a single highway with a whole city grid that redesigns itself.
Okay, now that we get the what and the how, let's talk about the upsides. Why would a company spend billions on this new paradigm? What are the real-world advantages?
The advantages are very specific and very powerful. They're aimed at things traditional computers are just bad at.
And number one has to be power.
Absolutely. First and foremost, we're talking about running complex, always-on AI systems on milliwatts, power budgets that are just impossible for today's deep learning models.
And that immediately unlocks true edge AI.
Right. Devices that don't need the cloud, that don't kill their battery in 5 minutes.
And that ties into the second big advantage, which is speed.
Real-time response. Because it's event-driven, the system has almost zero latency. That's critical for anything that interacts with the real world.
Like robotics?
Robotics, autonomous cars, advanced sensors. Anywhere a millisecond delay could be a disaster.
And what about the learning part? You said the learning is built into the hardware.
Which means these systems can support online, continuous adaptation. A traditional AI gets trained once in a data center, then it's done.
It's static.
Exactly. A neuromorphic system is designed to keep learning out in the field. It adapts to new data, to noisy environments. It can handle ambiguity in a way that deterministic systems just can't.
So, is this all just theory? Is it happening in university labs, or are there actual chips out there doing this today?
Oh, this is very real. There's a global commercial push. Probably the biggest player right now is Intel,
With their Lowy chips.
with Lowy 1 and now Lowy 2. These are large-scale SNN processors, and Intel is showing they can run complex algorithms with just orders of magnitude less energy than a GPU.
And IBM was in this space early, too, weren't they?
Yes, IBM's True North was one of the first really big platforms that proved that you could scale this architecture up to, I think it was 1 million artificial neurons.
1 million neurons.
Which was a huge proof of concept. And if you want something you can actually buy today for a product, there's a company called BrainChip.
What do they make?
Their chip is called Akita. It's an edge neuromorphic chip designed for this kind of real-time local processing.
1 million neurons, continuous learning, running on milliwatts. I mean, it sounds like the perfect computer. So why don't we have these in our phones already? There have to be some major hurdles.
There are. We're still very, very early. And the biggest challenge, by far, is programming them.
It's not just a new programming language.
No, it's a completely different way of thinking about problem solving. It's a massive understatement to say they're hard to program.
Why is that?
Because we're all trained to think sequentially. Do step A, then do step B. SNNs are parallel. They're asynchronous. They're probabilistic. You're not writing a set of instructions. You're designing an environment of neurons and hoping their collective behavior solves the problem.
That's a huge mental shift for developers.
It's an immense skills gap. And that's compounded by the fact that we don't really have the tools yet. There's no universal neuromorphic software stack. No Windows or Linux for these chips.
So everyone is kind of building their own thing from scratch.
Which makes it really hard to benchmark performance, too. You can't just measure instructions per second. You have to use new metrics, like energy per spike, which makes it tough for a business to figure out the ROI.
And the hardware itself, the memristors, they're not quite ready for prime time?
They're still early stage. Manufacturing them reliably at massive scale is still a major technological challenge.
But even with all those challenges, the potential must be huge to justify the investment.
It is. The applications are what's driving this. These chips aren't going to replace your laptop, but they will enable entirely new things.
So where will we see them first? Give us the highlights.
First place to look is robotics. We can finally build nervous systems for robots that react instantly, using almost no power.
Giving them truly biological level reflexes.
Exactly. Then you have autonomous vehicles, processing all that sensor data LiDAR, cameras in real time, without a trunk full of power-hungry computers.
And the low power aspect is perfect for wearables.
Perfect for wearables and medical devices. Imagine an AI assistant on your phone that's always on, always learning, but doesn't drain your battery in an hour.
Or what about in the body?
That's the really exciting part. Things like real-time brain signal decoding for advanced prosthetics, or tiny implanted monitors that can run for years.
And what about extreme environments?
Think deep space exploration, or remote security systems, places where you just can't go to change the battery. An NC system could do real-time event detection for years on a tiny power cell.
I guess the ultimate goal is brain-machine interfaces.
That's the holy grail. Chips that speak the same language as our own neurons, the language of the spike. That will be truly transformational.
So let's bring this all together. What's the big picture here? Our deep dive seems to show that neuromorphic computing isn't going to replace, your desktop computer anytime soon.
Not at all. That's the core insight. It's not a replacement. It's creating a new class of intelligent machine.
A specialized class.
A specialized one, built not to run software, but to quite literally imitate life's architecture. They're built for sensing, for recognition, for adapting to the real world at the edge.
Okay, so here's a final thought for you to take away from all this. We spent this whole time talking about this shift from continuous calculations to these event-driven spikes.
Right. And that shift fundamentally changes how we even define intelligence in a machine.
How so?
Well, traditional computing, it values the magnitude of the signal, the size of the data.
Bigger is better.
Neuromorphic computing, like the brain, shows that timing, that precise moment a signal arrives, can convey just as much intelligence, if not more.
So it's not what you say, but when you say it.
Exactly. Think about that. The silent intelligence that's embedded not in raw strength, but in the flow and the rhythm of signals.
Yeah.
That is the quiet revolution happening right now, inside the machine.